years ago, I would sometimes do like a whole lecture and the clock wasn't counting, and you get to the end and didn't record anything. All right, so today we're going to learn how to punch with our feet and kick with our hands. It's from the movie. In the karate class in the movie, that's one of the things they like, no. Now that felt like a punch. A very weak punch, but it still felt like a punch. All right, so actually a good lesson here would be how many of you are actually on Slack? Because did you notice that I put up the solution to the homework, what was last Friday? Because I wanted to make sure you had the right. Well, actually, the catalyst for it was Clancy not having a clue what he was doing. And he's like, look, I'm just confused. I don't even know what you're asking me to do. So I figure let's start with a core example, get everybody having it working, and now from this point forward, no more handouts. But out of curiosity, how many of you didn't even notice that I gave you the homework? Check Slack. There's your lesson. Check Slack, right? Okay, this was in 300. I mean, it was in the 300 folder. So make sure you're checking Slack often. Okay, because I will post things on Slack. I actually thought about sending out an email, and then I thought they should be checking Slack. So that's your lesson for the day. And we do put important stuff up on Slack, internship opportunities, and I'm not just making it up. Some of you have seen me post those things in general recently, and also conferences. And I'm taking some students to an artificial intelligence conference tomorrow related to their senior seminar project. But I mean, we do put legit things up there, and also Front Row Club announcements, obviously, which very sparse crowd up there today. What happened to you, Brocker? You used to come to Front Row Club.
This is my first class. I have to get up early. Oh, no.
This is my first class.
Ooh, yeah, that's tough. Unbelievable.
And I teach till 10 p.m. 2 nights a week. Yeah, suck less. It's the today's theme. That and the kick with the hands thing.
You should put just be in your general chat. So like your daily advice for today. Today's advice is suck less.
Well, I mean, several of you, I think I've said it in class before, but several of you know who hang out with me outside of class know I say that relatively often, right? And again, and I've done that for years. I posted this on Slack, 3 weeks ago maybe. There was actually it's the client for Blaine and Eric Poole from a couple called Aurora WDC, which is a data mining AI company. And we had dinner with him for Blaine to kind of get the gist for his project. And his T-shirt said "suck less" on it, so I took a picture of it and posted it. But now I actually have to hold him to it because I told him I need him to get me one of those T-shirts. And that's hard to find clothes my size. You got to go to the Canvas guy. I told you about my Canvas guy, right?
No.
Oh yeah, because I can't just go into Kohl's and buy a shirt. You know, because they sell shirts for like normal people, and I'm not a normal size human, right? So yeah, I have a guy at what's it called, Fleet Farm. He's a Canvas guy. He cuts everything out of canvas and he sews it together for me. Yeah, all custom stuff, burlap.
Yeah, that's what I always do.
All right. Like, I'm not sure if he's serious, but he might be. And that's what scares the crap out of me. He might be. All right. We use Ubuntu in here, or we use Raspbian? Ubuntu? Okay. It is disconcerting how ungracefully if you want to see, here's our current operating system in the 450 class. It boots up and puts one character on the screen using the frame buffer. So almost competitive with Windows 10 at this point. All All right, so we need to be in here. So let's close this. All right, so let's walk through what I put up, and then we're going to start adding stuff to it. I'm going to start closing down some of these tabs. This is OS stuff. This is actually an interesting thing I'll throw in here just from a, we've been talking about, we're working with C and C++, and we know, remind me, what does a compiler do? Go ahead. Yeah, well, yeah, so compiler goes from a high-level language to a low-level language, and the linker ultimately gets it to machine language, zeros and ones. And very rarely do we need to write anything in a low-level language anymore because we rely on our high-level power tools, like in here we're using C++. But every now and then, so for instance here in the operating systems class, systems programming rather, where we're writing an operating system, we had to write two functions in assembler. So this writes a single byte out to the screen, and this reads a single byte in from the keyboard. And we couldn't do these in C, so we have something called a wrapper. So we wrote them in assembly inside of a linker file, and then you create a wrapper. Where's my io.h? So these are the C functions that wrap those two assembly functions. So it allows you to write a function in assembly and then give yourself like an entry point in C to get to that. So kind of an example in the languages we're working with where you can actually do part of your projects at the low level and then the rest of it at high level when it makes sense. All right, so let's just get... Is this us? No. Well, it was us, but not us now, right? All right, this is us. Okay. So again, we have our header files here, and I think some of you, as I was reading through the papers for the what's changed from old school C++ to the newer renditions of C++, some of you talked about these HPP files. So traditionally, C and C++ use something called a header file. And we've kind of talked about header files as being this idea of almost looking at your interface. Here's my documentation for what my code will do. And then you actually implement it someplace else. So we're documenting it inside of HPP. Then we're implementing it in the CPP. All right. So a lot of times what you'll see is instead of it being a .hpp file, it'll be just a .h file, a header file. Now, anybody know from a couple people wrote about it, so we'll see if anybody admits to it, know where HPP comes from and when you might choose to use HPP? You never have to. You could always use .h files, but in your readings, what is the point of an HPP file as opposed to a .h file? Got nothing? So C and C++ are often used kind of interchangeably for a lot of projects, where you'll have some of your code that has to deal with the operating system level. You're making system calls, might have to be written in C, but you might choose to write your parts of the application in C++ so you have access to objects. That would kind of make some sense, right? So you might have kind of a mixed breed application that is C and C++. If you're doing that, you would usually use a header file, just a .h file, even though the compilers themselves don't care. Although an older C compiler probably is going to expect just a .h file, but a newer one will allow either one. Yeah, go ahead.
So the difference between HPP and H is that one has multiple code types and the other one doesn't?
I would say the trend would be this. A .h file would be for C project specific, only C. Not only one language, but specifically the C language. A .h file would also be used for a mixed file format of C and C++. .hpp kind of indicates that, so we can call this a naming convention, that your project is pure C++. So that's where the HPP comes from. So we're doing C++ specific header files, even though we can rename these .h if we wanted to, and then instead of including node.hpp, we would just include node.h. The compiler doesn't care, all right? But we're following kind of modern naming conventions, even though you may not necessarily see this in the wild that often. All right, so if you remember from last class, we designed our node object. So a node, we decided, was going to have a payload, and it needed to have a pointer to our next node. All right, so let's look at how we've implemented this in C++. So just like in Java, we have all of our fields. We start off as private, then we loosen them, loosen the reins as we need to. All right, so we have a class called node, and again, this is just our interface for it. This is going to define what's going to be in there. Then over in the CPP file, we include that interface, and then we build it out. This is our implementation for that HPP file. Make sense? All right, so in our header file, we're saying we're going to have two private fields, one for payload, and one is going to be a node pointer to our next node. Then we're going to have 4, in this case. We could have fields in here if we wanted to, but we're going to have 4 public methods as well as 3 methods and a constructor. So our constructor for node is going to take in a single integer. Then we're going to have a getter for our payload, because payload is a private field, and we might externally need to be able to get at that private field. So we're going to have a get payload function that's going to return an int. We're going to have a get next node function that's going to return a node pointer. So these are getters for these 2 private fields. And then we're going to have a set next node function that takes in a node pointer and will set the next node equal to that. That's its purpose. All right, go ahead.
Is there like a Java equivalent of the node pointer? I guess I was just getting confused with the memory address.
Well, yes. Java, remember, Java does not have a syntax for pointers. So the Java equivalent would be that. Okay, but keep in mind that in Java, we've seen the address for a node or a random or something get printed out, so we know that it actually holds a memory address, but we do not have the special syntax, the star or the ampersand, for directly dealing with memory in Java. Java either says this is an address or it's a value. In C, we can choose to have this guy not take in a pointer to a node. Remember, this goes back to our conversation of C++ empowers the programmer to make dumb decisions. Nothing says I can't write that. Now I'm saying this function requires, you remember our example, you're inviting me to your party, you hand me the house. Now this method says, when you want to set the next node, you give me the node. Not a pointer to it, the actual node with all of its heavy stuff in there, whatever. All right, so C++ empowers us to decide what makes sense. Do we want a pointer to this guy, or do we want the actual node? And we would say in real life, if we assume nodes are kind of like houses in that they're heavy, it would probably never make sense for us to receive the actual node. Instead, just give me the address where I can find it. Make sense? But C++ empowers us to choose because we have the syntax for it. That make sense? All right, so these are our methods we're going to define. So any questions on the header file for node here? All right, so this guy, even though we didn't mention the methods that we were going to write down here, we said a node's going to be these fields, and now I kind of put in the supporting methods that are going to help us build nodes, access our payload, and read-only access to our payload, and read-write access to our next node. All right, that's our supporting players here. Now we're going to take this as our template, and we're going to come over here and we're actually going to implement it. All right, so we're including the header file. So we're saying that guy has defined our structure for our class, and now we're going to implement his various parts. So here's our constructor. We've defined that we're going to have a public constructor called node that's going to take in a payload as a parameter. So I am, for the node class that was defined in this header file, I am implementing this function. Go ahead.
So on the HPP, we established that there are class functions that we're developing, and then on the CPP, we actually detail what they actually execute. Is that basically what we're doing?
Yeah, I wouldn't call these class functions. I would say the header file here, this is the header file. So the header file defines what our class will have in terms of its fields and its methods and constructors. The CPP file is the implementation of those things. So we can also basically look at this as documentation, right? If we look at just the header file, we say, oh, what's a node? Well, it's got a couple of fields, and it's got one constructor, and it's got 3 methods. This guy paints that picture for me all in one thing without all the extra implementation kind of muddying the waters. Go ahead.
So I had an issue with my code where it, like, after compiling it, it basically dehighlighted it, made it like less brighter, and it said, well, let me see if I can get the message.
Are you talking about like these colors became different?
Yeah, so it's like, hold on, let me look at the actual message here, because it's might be easier. Okay. So it's like, there's like a light bulb that says, disable inactive region colorization.
Oh, I don't know. It sounds like it's a Visual Studio Code setting or something. So not a C++ thing. I mean, we could look at it later or just Google it, but it's not a C++ thing. Yeah.
What is the difference between the first 2 lines?
Which 2 lines? Oh, these?
Yeah.
Oh, so these guys say if we have not defined a node header file, if there isn't previously defined a node header file, which we know we haven't defined one, then this is our definition of it. So this is an if statement. If this is true, if we've not defined a header file, then define it. This is what it is. And here's the end of that if. It's just compiler directives. So for right now, you don't have to worry about it, but this might be in a situation where you might import somebody else's library and they might have a node. You can choose to have it yell at you in the case where it's there's a duplicate, and then go and deal with it. So kind of wrapping this is almost like self-policing your code. It's like if it yells at you and it says, oh, there's already one of these, and you're like, oh, well, let's look into that and figure out what's going on. Okay, so in our node CPP, this is our actual implementation. So our constructor for node is going to take in an int payload, and we're going to set this guy's payload equal to payload. All right, and this is a node pointer. All right, so it's a pointer to, so this is a pointer to the address of this particular node. So I can either say star this dot payload, or I can say this payload. So this guy is syntactic sugar for this. This says, give me the actual node that this points to. So star this says, resolve the memory address to the node. Then with that node, give me access to his payload. This syntax right here with the arrow is shorthand for all this parenthesis stuff. So it's saying this, give me the value of this, the resolved value of this, dot his payload.
In C, the arrow is actually for memory addresses, though, right?
Same thing.
Same thing.
Yeah, I mean, that's what I just explained. So this is a memory address. Star this is the value at that memory address.
Okay.
So that's the actual, in this case, we're inside of node. That's the actual house. That's the actual node in this case. And if we have an actual node, we can then use the dot notation for setting its values. But if we don't have an actual node, so for instance, I can't say this dot payload. This is a memory address. So this would be like saying 0x123ABC dot payload, something like that. And memory addresses are primitive types that only hold a value, right? They don't have functions and fields and things like that. So that wouldn't make any sense. But if we say star that says follow that memory address to the actual object that lives there.
Okay.
And then give me that guy's payload.
Okay.
All right? So this is, yeah, I call it syntactic sugar. So whenever you have a pointer to a pointer, you can use the arrow to resolve the first pointer to give you the value. All right? So I'm going to say this node's payload is equal to payload. We've seen that in Java, right? Now I'm implementing get payload. Same exact thing. Get payload is going to return an int. We're implementing in terms of our node class. The method's name is get payload, and we're going to return this dot payload. Get next node returns a node pointer. Notice again, we're using the syntax. Node pointer says I return the address of a node, not a node itself, the address of a node. Go ahead.
So if you were to just say return payload, would it just send you the address?
You mean up here?
Yeah.
Well, payload is an int type. So ints are primitive types. We're not storing an address. If I wanted it to return the address of that, I would have to say int star is the return type, and integer pointer is what I intend to return. And then inside of get payload, I would return the address of that guy's payload. Because I'm returning an int pointer. Okay, so understand in C++, we've introduced this syntax for directly working with memory. Hopefully, we make very similar decisions to what Java has already made for us in our experience with Java. That is, if I'm returning a primitive type, we're probably going to just return the primitive by value, because primitives are light, correct? If you're inviting me to your house, you're not going to hand me the house, you're going to tell me the address of the house. But if I've asked you for a quarter, you're going to hand me a physical quarter, not a piece of paper that tells me where I can go find a quarter. Make sense? We can make that decision in real life. Okay, so things that are light, it makes sense to just hand them the actual thing. Things that are heavy, we might tell them where they can go find it. Real life example, right? Java made those decisions for us. C++ and C, we have to choose. Am I passing an address or am I passing a value? And that's where we have that star and the ampersand syntax for making those decisions. So since I want this guy to return an int, I'm going to return this guy's payload, which is an int. And I need to make my syntax there match up. So get payload returns an int primitive type, so it's actually going to return the value, an int. All right, and here's my definition of that. Returns an int, called get payload. We're implementing something from the node class. We're just going to return this guy's payload. Get next node, it's going to return a node pointer, the address of a node. Implementing this from the node class, we're going to return this guy's next node, and next node is a node pointer. We don't have to resolve it or anything. It's already that kind of value. It is a node pointer. I'm going to return that node pointer. Okay. And then set next node. This is going to take a node pointer as a parameter. So the address where you can find a node, and it's going to set this guy's next node, which already is a variable capable of holding a node pointer, the address of a node. Next node holds the address of a node. That's what that guy holds. So set next node will take in a node pointer. I will set this guy's next node equal to whatever was passed in, because they're both node pointers, and he doesn't return anything. Oh, all right, so make sense? We're starting to see the pattern here. Okay, Java made these decisions for us. Now in C++, we have to decide, is something a value or is something an address? And we kind of make that decision right off the bat. We say that, oh, that's my quarter. If you're going to give me the value stored within a node, you're going to give me the actual value, the int. So I'm going to represent that field as just an int, not the address of an int. It's just the whole int, the actual value. Whereas my next node, I'm going to say this guy is an object. Objects are big, so I'm going to represent him as the address where that guy can be found in memory. Make sense? Java does this automatically for us. If we had the same line in Java, it would have been node, next node, and Java treats this as a node pointer automatically. Because Java's removed that syntax from us. But Java will treat it in this identical way that we're writing it. Okay? So that's my implementation of nodes. So nodes now know how to hold a couple of pieces of information and know how to get and set those things. Linked list. Here's our header file for a linked list. We're going to keep track of two pieces of information with a linked list. That is the address of the front of the list, a node pointer. That's an address. Okay. See, this is a self-fulfilling prophecy maybe. Do you see how we're already kind of intimidated by these addresses? Okay. Even though we've been working with them for 2 years, or I guess a year, right? 2 semesters. Now that we have this special syntax where we're purposely making the decisions, it's intimidating for us. This is a variable. This is the kind of value that variable holds. This is a variable. This is the kind of value that variable holds. This guy right here says no more than the kind of value head is built to hold is the address of a node. The kind of value count is built to hold is a physical integer. If I had changed this to int star, now its count is built to hold the address of an integer. No more. Just what kind of value am I going to find in that box? All right. So don't put memory addresses up on this crazy pedestal that they're this amazingly difficult thing. It's a thing. Just like an int is a thing. Just if we have a memory address and we want to do something with that, if you want to pick up the keys from a house, you have to first go to that house, then you can get the keys. Go ahead, Sarah.
So is the reason why we don't do the pointer for the end that concept of heaviness versus lightness? The end
Yeah.
so light?
We could, though.
Yeah.
Nothing prevents us from doing it. We're just making an implementation decision that, ints, memory addresses, they weigh kind of the same or ish. They're close enough for darts or something like that. So we're just, as the implementers, we're making the decision that we'll just pass the value. And that comes with the consequence of if I make a change to it inside of a function, that change won't necessarily be permanent. It is when I say this dot, because I'm changing the guy that's the thing that's owned by the class. But otherwise, if I pass an int value into a method and I make changes to that int value, those aren't permanent changes outside of there. I'm kind of getting a copy of it and then making stuff. So if I have 2 quarters in my pocket, or I'm some kind of magician, you ask me for a quarter, and I duplicate my quarter, and I give you one of those, and you go away somewhere and you bend it. The quarter that's still in my pocket, its duplicate, will not be bent. They had nothing to do with each other once I gave you a copy of it. Make sense? So that's this version of it. If you ask me for a quarter, so maybe this is called get quarter, and I duplicate my quarter, and I give you a copy of my quarter, and you go and damage that in some way, my original is not damaged. They were not linked anymore. Where if I had given you, you know, my hiding place where I keep my quarters, and play that in your head in the creepiest way possible. Okay, I tell you where you can find my stash of quarters, but I only have one quarter there because I'm weird, right? So this is where you can find that single quarter. Okay, and Sarah goes over there and damages that quarter. Later on, when I come to my stash, I'm going to see that I have a damaged quarter. Okay, if I give you the address of my house, you go and spray paint my garage, I'm going to get home to a surprise. Make sense? All right, no ideas, Brocker. All right, question back there?
So the thing I had the biggest problem with when I was trying to write out this was trying to figure out how to assign addresses, how to reassign the header's address so that it.
Okay. Yeah, we're going to walk through the logic of it.
Okay.
Yeah, so we're getting there. I just want to really emphasize this whole pointer versus not pointer thing, and don't put it up on some sort of crazy pedestal. It's a value. It's either a memory address or it's the actual thing. They're both just values. If it's a memory address, that just tells you I need to go there first to get the value. If I give you the address of my house, you can't just wave your hands and paint my garage. You have to go to my house first, then you can paint my garage. That's all an address says. Travel there first. Okay? So in linked list, we're going to keep track of two pieces of information, the front of the list and how many elements are in the list. Then we're going to have a constructor that takes no parameters because it's just going to create the empty list. And then we're going to have the ability to add front. This is what the homework was. Add front, taking in a payload, the new value I want to add to the front. And then we'll also have a method called display, which you didn't have to do for your homework. I just gave it to you to kind of prove that it worked, right? So now in our implementation of this guy, here's our constructor. All we do with the constructor is set our count to 0. There is not a head of the list yet, right? It's an empty pointer. Add front, we're going to take in a payload. This is the value, the number we'd like to add to the front of a list. The very first thing we're going to do is we're going to build a brand new node. This is equivalent to node n equals new node payload in Java. Go ahead.
So even though this is C++, we're not using Alec yet?
Not yet. We could. We will at some point.
Okay.
Yeah. This is the friendlier starting point for it. This, no new definition. This creates memory for us. All right. So this is the equivalent line in Java, but all this is saying is Java has removed our syntax for pointers. We know that if I were to print out the value of n right after this line, it'll be a memory address, which is no different than me saying n holds a memory address. Does that make sense? In C++, we are making that decision to hold a memory address, where Java made that decision for us. In both cases, we likely should hold a memory address to something heavy. All right, so we're going to create a new node using the payload that was passed in, and now we want to put that node somewhere. We ultimately want it to end up at the front of our list, right? So this dot head, by saying not this dot head, what we're actually testing here is to test the pointer count of this dot head. So this guy returns false, or actually we're going to say boils down to 0 if nothing points here. Okay, so head has a count. Number of things point to that front of the list. And right now there is no node there, so the pointer count for head is 0. 0 is false. That's why we're saying if this guy is false, not false is true, then we'll just go ahead and make head point to this new node. So this guy right here asked the question, if head currently points nowhere. We could write this differently and say not equal to 0. That make sense? But since C++ stores Booleans as zeros and ones, we do have trues and falses as like syntactic sugar for it. But under the hood, it is numeric, and 0 is false. Not 0 is technically true. Typically, trues are represented as ones, but the guaranteed way is not 0 is true. Go ahead.
So it basically checks if there's nothing there. So then it then moves to then try to put whatever n has in its.
Yeah, here. The equivalent here in Java would be this dot head this dot head equals null.
All right.
So if the head points nowhere, then we'll go ahead and make the head point to our brand new node. And then magically we now have a list with something on the front of it. Go ahead.
Could you use count equals to 0?
We could, in this case, because we have decided we're going to keep track of count. But we are asking the question in a different way. Instead of looking at the front of the list and say, do you point anywhere? We're instead going to look at our variable count and say, are you still 0? If you're still 0, then I know that I don't have anything in my list, which means that head should point nowhere. So they both ultimately give me the same answer. We're just getting to that answer in different ways, right? Go ahead.
So we didn't like define head before that. Does it automatically start? At
It'll
0?
start off as a pointer count of 0.
Okay.
There's a thing called null with all, I think it's in all caps in C++, but we'd have to import standard lib in order to use it. It's a syntactic sugar thing, so I didn't want to muddy the waters. All right, so here, I'm going to go back. This is pretty common code that you'll see. So if not this head, that's the shorthand way of saying if this pointer points nowhere. All right, so if this pointer points nowhere, then make this pointer equal n, which is a memory address. This guy's capable of holding a memory address. N is a memory address, so we will go ahead and put n's memory address into this variable right here. Make sense? All right, this is a variable. It's capable of holding a memory address. This is a variable. It's capable of holding a memory address. In fact, it does hold a memory address. So n holds a memory address. Head is capable of holding a memory address, so we'll put the value of n into head. Okay. No different than Java. We just have a couple of stars and asterisks strewn about. All right, so if my list is empty, if list is currently empty, do that. Else, list has at least one thing in it. If list has at least one thing in it, what are we going to do? Well, we're going to make n. So let's draw the picture here. We actually did this last time, right? Let me just steal this slide. And I'll dump some of these things. All right, now I have a variable called n, and n points to my new node I just created. That's this right here. N points to that new node. First question we ask is, if head points nowhere, which right now it does, it's pointing out to nowhere, then just make head point to this guy. Done. If head points nowhere, make head point to the new guy. Now, if this is what our picture currently looks like, and just for the sake of spacing, I'm going to make head point to the front of that list there. Okay, so right now my list looks like this. I've created a new head. I'll just make up a memory address there for it. All right, so I just created my new n. That's this line right here. Then I ask the question, does head point somewhere? Here's head. Oh, and count is currently 1. Yes, it does point somewhere. So I can't just make head point to the new guy. If I do that, I've lost access to this guy. So instead, what's my 1-2 punch? I first set n's next node equal to whatever head points to. Here's n. Here's his next node. I'm going to have him point right there. Then I'll make head point at n. Make sense? And now I have added this new node to the front of my list. Whether I did this or I did this, my list has one more thing in it. Count has gone up by 1. Go ahead.
So initially with the if statement, since there's nothing in it, it would go to n, which tells it it has a payload of 5, and then its node is named as 200. So that's added to the list, and then else would tell it.
Well, I mean, you're filling in a lot of gaps there, because this is generic code.
Okay.
If head points nowhere, set head to point to whatever n is. We don't know what head's payload is. It's whatever was passed into this method. Okay, so this code is written generically, so whenever I say add a value, add a number to the front of the list, it will create a node, and it will one way or another get it to the front of that list.
Okay.
It'll either make head point right to it, or it'll make that guy point to what head points to, then make head point to it. All right, so that makes sense for next node, or for add front rather. So that's my add front. And then I wrote a little display method. What does my display method do? It creates a variable called curnode and makes it point to the same place head points to. So curnode points to the same place head points to. Then I'm gonna, in this case, I am using count, right? I don't have to. I can just traverse it until I run into a node whose next node is equal to 0, right? But instead, I'm gonna go ahead and use my count. So I'll start off at head. I'll go through count number of times. So I'll repeat something count number of times. I'm going to use cout. So this is from the standard library. Actually, I should be able to use that from IO since I included IO stream. Is cout not in IOStream anymore? Do I have to use standard template library? No. We'll look into that. For right now, just write it that way. All right. So this is going to write something out to the screen. This is our system.out.println. We're going to write out the payload of cur_node. So whatever cur_node points to. Right now, cur_node is pointing to this guy, which has a payload of 5. So it'll print out 5, followed by a carriage return. Then I'll set current node equal to his own next node. Cur_node is this guy. His next node is this guy. So cur_node will be equal to his own next node. Do it again. Print out the 9. Cur_node is equal to his own next node. Now it points nowhere, but we've also run out of counts. Okay, we just did it twice. Count is currently 2. We've displayed the contents of our list. Make sense? So that is add front with evidence that add front is working with the display method. So when we get over to our main CPP, I'm going to go ahead, I'm including linklist.hpp. That tells me how I can use linked list stuff. So I'm going to define a brand new linked list. Then I'm going to add a 1 to the front of it, which makes head point to that 1. Then I'll add a 2 to the front of that. So that makes this guy point to what head points to, and then makes head point to him. And then I'll display. So this should display a 2 followed by a 1, since I'm adding to the front. Go ahead.
So where I got lost in this was trying to decide whether or not to create a header file for main. So why don't we do that once it all works that we don't have a header file?
Oh, so all programs begin and end with main, and main just has our int main in it. We have nothing else we're implementing. If we did, so for instance, you'll find a lot of examples in C++ where they actually embed the classes inside of this file, which might be fine for something of this size where we have our linked list in Node and they're not too complicated, although we're going to start seeing that linked list is going to start getting bigger and bigger. But that main method, this is our driver .java that we had in our other examples. You're late.
Crap. I really thought it was at 11.
Killing me.
I was like so pumped walking in here early.
Oh.
Oh, you're like,
So we have our, but yeah, that's the punchline. Is it's because main this is defined. We don't actually have to call it main CPP. We can call it whatever we want, but it's the file that has our int main in it, which drives our program. So we can almost think of it as like a special case.
Okay,
It's-
so we don't even have to put that in the linked list.hpp, is that right? Like we don't have to put that in the header file?
This guy here.
No, main, as like the main method.
No, because this guy, correct. This guy is not, so main here, we're not implementing something that was defined inside of header. If we were, we would see, it would say linked list : main, like that. So we're not actually implementing something that was found inside there. Main is its own special thing. All programs begin and end with main. All right, so create our linked list, add a couple of things to the front. So when these 2 lines are done, 2 will be in the front, 1 will be next. We'll tell those guys to display themselves. Let's go ahead and run this. All right, let's see, I have my linked. So there's my linked list file. So you actually could get away with just saying g++ main.cpp, I believe. No, it's going to want me to do all the star.cpp. So that says compile all the C++ files. That gives me my a.out, so ./a.out, and there's my 2 followed by my 1. Go ahead.
Okay. So what the A dot out, how does it know that which file to what?
Because of what we literally just explained. That's the all programs begin and end with main. It's going to look for that specific main method. So as part of that G++ thing, it's going through compilation, which takes your high-level language to a low-level language. Then it's going through something called a linker, which actually builds your executable. And what the linker does is it brings all those things together, and there should only be one main. And that's where our program will start, is in that where that one main is.
So that file, it doesn't have to be called main CPP, but that method does have to be called.
Correct.
Okay.
Correct. And specifically, it has to return an int. It can optionally take in the command line arguments. That's why I've left them out here. But it does have to return an int because traditionally C and C++ programs have a return value because they are used for writing command line type things. Yeah.
Is there a way to make it called something other than a.out?
Yeah. So if we do G++, let's just do -h -- help. I think it's dat-o. Place the output into another file. So we can do that guy and then do a -o my exe, something like that. And now I have a file called my exe. Go ahead.
Sorry if this is misunderstanding something you just said, but didn't we call like the main kind of idea driver in another place? Like, does it have to be called main or?
No.
Okay.
That's the point. So in like Java, we always called it driver.
Yeah.
Here, we're naming it main.cpp. That kind of gives us the hint that that's where it is. It would be perfectly acceptable for me to call this guy, can I rename it here?
So like to Josh's question though, it would still be able to find it even if it's not called main.
So now I renamed it driver CPP. So now I should be able to compile that guy and call my exe, and it still runs.
So is a.out just the
Default
default?
executable.
And then so what if you had, so I put all my linked list files in its own folder, and all my dice files are in a different folder. What if you had like two a.outs in the same folder? Is that
Well, you would never have two a.outs in the same folder because the second one would overwrite the first one.
okay?
But you could have two different executables in the same folder that were built from, nothing keeps me from taking my exe file and moving it into a folder with a bunch of executables. In fact, we see that here if I go to ls user bin, these are all executable files that are part of the Unix operating system. So that's just a folder of executables that are all our system calls and things like that we know how to do. So ls is in here. Actually, is ls in just user bin? Or /bin, rather. Yeah, ls is in /bin. So /bin is your Unix core binaries, and then user bin is user level binaries. But those are all compiled files from somewhere, and then just moved all the executables into a couple of folders that are in our path. So that when I type in ls, it's actually finding, if I say which ls, it's telling me I found that in /bin ls.
So say all the dice files and all the linked list files are in the same folder. When you go to compile, you have to specify only compile these ones.
Correct. Yeah, you wouldn't be able to do the star.cpp thing.
Okay.
Yeah, you'd have to tell it the dudes that are involved in your particular application. Yeah, so you can have two different CPP files in there with main, but you can't compile more than one of them at once. Yeah.
What is it? .hpp.gch file extension?
.gch.
http.gch.
Oh, it gives you an output. It's probably a. I'm guessing it is intermediate code, so it's probably the step between the compiler and the linker will use that to make its ultimate executable. So when are you seeing that?
When I like after I compile in my directory.
You compile the HPP file.
Yeah, it's very like the machine language.
When you do
pull it up.
C++.
Yeah.
Oh, so then that's what it is. Yeah. So if it's machine language stuff, what is it? Machine language or low level?
Low level.
Low level. So it's assembler code looking stuff.
Yeah.
Yeah. So it's then what I said. It's the intermediate step before it becomes machine code. Yeah, which is actually, so if I say G++ and I say linked list.hpp, you're saying it's that. So that guy gives me this dude right here, and I say more linked list hpp dot that. This is showing me the actual low-level code for that the linker will then use to build my compiler. So we're seeing the output of the compiler. All right, that makes some sense? Or at least more sense? Go ahead.
Could you make a functional program with just CPP files, or the header files required?
Header file is not required. You can actually just put all the stuff that you have inside the header. So I can take all of this, and I can take this and put it inside of a CPP file and then explode it out. Yes, you can do that. The downside with doing that for small projects like this, there probably isn't a significant downside. But the reason that C and C++ typically follow this header, and because nothing keeps us from inside of driver here, I renamed it, from saying include that. That just says paste the contents of that file up here. Okay, that's all that's happening with that include. So the reason to split things into header files is when you have like a really large project like an operating system. If you're going to build the Linux operating system, which has thousands of files, right? And let's say you go and make a little tiny change to just one of those files. All the other ones have already been compiled and turned into machine code. That one little file needs to be recompiled. If you have everything inside of CPPs and they all rely on, that CPP file will now have its object code and it relies on 10 other header files, all of those then need to be recompiled. Where if you have the header files and you see that, okay, this guy relies on this header file, it's only going to recompile that one CPP file or the couple of files that rely on that header, and then it'll just relink all of the previously compiled stuff with your newly compiled stuff. So for like Linux, that might take 20 minutes to compile, for example, or longer. I haven't compiled Linux in years. It used to take a lot longer. I'm just estimating for modern computing speed. But it's not going to be something that compiles instantaneously. It'll take time to compile. And if you have one little bug, you might have sat there for 18 minutes waiting for this thing to build. And you get one little bug, you go and make a change, now you have to spend another 18 minutes. Instead of just picking up where it left off or going back a couple of steps to, anything that's reliant on what you just made the change with, and then continuing on. Does that make sense? Okay. So, any other questions? Go ahead.
So can you use header files with other languages, like Java, Python?
Java doesn't support it. I don't think Python supports it. The short answer is probably. There's probably some language that does support it, but C and C++ are where you see them. All right, so let's go ahead and let's add to our linked list a remove front. All right, so maybe remove front is just going to return the payload from the front. Actually, let's write a couple of things here. Let's have something called get front. And get front is just going to give us the value that's at front. okay, as opposed to actually removing it. Just going to hand it to us. It's going to say, look, this is the value that's at the front of the list. But we'll give it the actual payload, not the node. And then we're also going to have a int remove front. And that guy will actually disconnect the current front of the list, making the guy it points to the new head of the list, and then ultimately return the payload that's in it. All right, so 2 new guys here. So we added it to our linked list HPP. We'll go into our linked list CPP, and we'll put them up here. So this is linked list. And notice the linked list part comes after the return type. All right, so the return type's always in the far left. Then we say we're defining the function of linked list. All right, so get front is, it's going to be a little weird how we implement this. For right now, just so we're just going to assume you wouldn't be calling get front unless you had a list with one thing in it. Fair enough? All right, so we're going to just say return this dot head, okay, which is the node that lives at the front of the list. All right, so this dot head. Now, if this guy, so head is a value that has and head is a node pointer, correct? So if I want that node pointer's payload, I'll say get payload. So this is a pointer to a node. So to get to that node, we're going to say this arrow. Here's the head for that. Head is also a pointer, which has a get payload. So we'll return that payload. And actually, for right now, let me just get rid of remove first. We'll just do one thing at a time.
So this, when doing this head and then get payload, you point to a memory address and then pointing to the value.
Yeah, and we'll draw a picture here in a second.
Okay.
All right, so I'm going to say instead of display, let me do a LL get front \n, something like that. It is C out, right? Oh, I still need to include IO stream. Yeah, so it must be down one more level. So there must be an IO stream.standard or something like that. That's now there to get to the C out. So I'm only going to look at the front. So I'll go ahead and do g++ star.cpp. Get front. And what did I? Oh, I wrote get front. That guy's good. Oh, hold on a second. I wonder if it's not recompiling the header file because I had that guy in there. Yeah, there we go. So, because our example before with all the assembly code stuff in it, because that we already had the intermediate file, it wasn't recompiling that file, so it was using our linked list version that did not have that stuff in it. So there's our front, which is the 2. Make sense? Okay, so similarly, we'll have our remove front. So this guy, I'll also have it return an int, because very rarely are we actually going to want the node. You know, when we remove something, we want the value that came off of that, but we also want to rely on it now being disconnected from the front. So we'll call this guy remove front, like that. And we'll go ahead and implement it over here in linked list. All right, and this guy is this dude here. All right, now to remove something from the front, and again, we'll assume that there's something in the front. We'll talk about error checking later. So you're only going to call this if you have something that's not the empty list. We want to go back to our picture here. So if I say remove front on this guy, I need to have something point to the guy I'm going to remove. Then I can reconnect head to that guy's next node. Then I can take this guy's next node and have it point nowhere. Then I can return the payload of this guy. Okay, so 3 steps. All right, so we're going to say, for remove front, we're going to say node pointer, call it node to return. We'll set this guy equal to this head. So he points to the same place that head points to. Then we'll say this head is equal to this head get next node. So we'll make head point to his own next node. So that did this move. So here's our node to return. Then head points to his own next node. Okay. Now, right now we don't, I haven't introduced null yet, so we're just not going to actually do this disconnect. We're going to lose track of him in a second anyway, so it's not the end of the world. All right, so we'll that last disconnect piece we're going to accomplish this way. So we've now updated our list, so our list is now, let's say, correct. Then I'm going to say int val is equal to node to return get payload. Then I'll delete node to return, and then I'll return val. Okay, so this cleans up that memory that we disconnected. Rather than relying on automatic garbage collection. So I'll go back here to our driver. We'll call remove front here. Then we'll also say LL display. So it should now show the list only containing 1 when that is done. Didn't put parentheses around it. Oh, the segmentation fault's from when we deleted it. That's where I'm gonna have to show you the null thing. But there's the thing we removed from the front. There's the one. So for right now, we can just make a mess of memory. Oh, that's still... Is that from deleting the linked list? Oh, remove front does need to. This is actually okay. We do need to say count minus minus. Our count did just go down by 1, right? Instead, we're getting a segmentation fault for display. That's like a null pointer exception because we are going through 2 times when there's only one thing in there. So there's our 2 and our 1. All right, that makes sense? All right, so for Thursday, we're going to write void add end int payload and int remove end. Or why don't we also do int get end? Those two will basically be equivalents. Homework. 3 methods below. Make sense? All right, so that's for Thursday. Turn in the GitHub. I'll upload this back to GitHub. So the link I have on Slack from last week, you'll be able to click on again and see the updated code from today. Questions, comments, concerns, bribes? Go ahead. I would say don't add tail yet. If you really want to implement it that way, that's fine. But right now we're using what's called a singly linked list, so we get to everything through head. So my intention here is for you to start at the beginning of the list, traverse to the end to remove that guy, not know where the end is with a tail. So don't use tail. Today's student, faculty, staff Bible study. Got in, grub, go to the cafeteria, sign in, get free lunch, take your tray down to the terrace room. Computer science usually has a table in there, so we'll save a seat for you.